So I'm going to talk about transactional streaming. Who am I? I'm the first developer on the VoltDB project. I've worked at a couple of other data startups. I've made a lot of mistakes, and I'm a firm believer in that's how you learn how to do things. So at this point, I almost know what I'm talking about. This is the first time I've given this talk. So if you guys have any feedback or how to make it better, stuff that didn't work, I would love to hear about it. So please reach out to me. I'm going to start with operations at scale. And everybody kind of looks at this a little differently, but I'm going to define what I think operations at scale are. So we start out by ingesting data from a lot of different sources into a horizontally scalable system. We have to process that data when it arrives. So common things we do are transforming, correlating, filtering, aggregating. These are really common things to do to data when it comes. The operational part is that we need to understand that data, and then we need to take action and record that action. That's the part that makes this operational and not just a pure streaming analytics solution. We also want to move relevant data to a downstream big data system, right? Whether we're working with Hadoop, like so many people here are, whether we're working with OLAP systems like Teradata, Vertica, et cetera. We want to move data into those systems for more big data analysis later. So it really boils down into how do we manage data movement, how do we manage processing logic, and how do we manage state management. And the most typical way people do this is they sort of go to the Apache menu, they select a whole bunch of things, and they start gluing them together. You end up with something like this. This is one example. There's a combinatorial plethora of ways to come up with different examples. But this is a real system that's in production in a lot of places. And I think of it sort of as a Rorschach test. If this seems like something that is very exciting to you, I'm going to try and talk you out of it. If it seems like something that is a lot of work and maybe you're looking for a better answer, I'm going to hopefully address that as well. So right now there's 16 talks wide, so I definitely thank you guys for coming to this one. So here's my talk here, transactional streaming, and next to it is building real-time data pipelines with blank, blank, and blank. And it's weird because this talk is at every conference you go to. Sometimes the conference will have several of these talks. My apologies to Todd Lipcom because I rewrote his talk. And all of these talks have the same theme, which is maddening of, look at this incredibly hard thing we got working that almost works. And we spent a tremendous amount of effort into it, and hooray, it almost works. And tomorrow we're going to do something different because we have some slight change in requirements that's going to require us to re-architect the whole thing. So my colleague and co-founder of Volt, Mike Stonebreaker, is a big proponent that one size doesn't fit all. This is an idea that sort of almost everybody accepts at this point. But say you've got analytics and operational data. These necessitate different storage engines to be more suitable. So analytics uses columns. Operations use rows. It's sort of a Vertica versus VoltDB kind of view of the world. A big advocate for using specialized systems. So machine learning is another case where you want dedicated machine learning systems, multidimensional math, search. All of these things have their own specialized systems that can be better than the general purpose systems. So is that contradictory with me saying that these sort of pick a whole bunch of dedicated systems and glue them together is the best solution? Well, it's a little different because what we're talking about is leading edge operations. Specifically, we're talking about operational stream processing and operational state. And I'm going to argue that this is a place where integration is not only possible technically, because both of these things fit together well. We don't have a columns versus rows problem when we're talking about operational stream processing and operational state, but it's also very, very smart thing to do. So what's the difference between all the places where you should use the best in breed tool and glue them together and operational stream processing? So non-integrated systems means that you have to write glue code or you use someone else's glue code. This is true no matter what you're doing. If you glue two systems together, either you find some off-the-shelf tool to glue them together or you do it yourself. Operational glue code is different than batch glue code. Batch glue code has some huge safety nets that make it amazing. This is why there are so many different tools that all use HDFS, because HDFS is this magical safety net glue. It's like the net under the trapeze artists that also tastes delicious. I don't know. You have immutable data sets in HDFS. That means you can experiment and you're not going to lose. Right? You can take a data set, you can mutate it, you can write to a new data set. The original data set is safe. You can always blow things away and reload. This is not always strictly true, but in a lot of cases, you could say, I made a mistake. I'm just going to fix it by starting over. And a lot of this comes because there's a lot less time pressure in these batch-oriented systems. You've already said, well, it's not going to happen in milliseconds. So if it takes 1 minute most of the time and now it takes 10 minutes, it's probably not tremendously impactful to your business as long as that's not super common. But let's look at operational glue. So back to sort of this example, and I've simplified it. I've got Kafka into Storm into Cassandra. There's probably thousands of deployments of this in the world. So Kafka, lots and lots of users, tested really well. Storm, lots and lots of users. If there are bugs in these things, in Cassandra, in Kafka, and Storm, people are going to find them. People are going to fix them. If you're using bleeding edge features, maybe you're going to run into them a little bit more. But there's a lot of use cases for this. So you've got this code. Maybe this is off-the-shelf code that you got, either from some community-supplied thing. Maybe you work with Confluent. And you've got this glue code. There's a lot of users here, but still way fewer users than Kafka or Storm. This is automatically a little bit more risky. This thing, you wrote this. You're one user. It's for your app. This is almost certainly going to be the weakest link in your stream processing system. So you say, I'm not writing glue code. I'm just using the well-tested Cassandra driver in my well-tested Storm deployment. All right, you're using a computer network. The Cassandra driver is talking over a computer network, and computer networks are not reliable. If you don't believe me, you can Google for computer networks are reliable, and a bunch of people will argue with you on the internet. Storm might fail in the middle of this processing, right? Does your code handle that? Cassandra might fail in the middle of this processing. Does your code handle that? Both systems are tested individually to keep going after failure, but your specific processing code that uses the Cassandra driver and Storm logic in Java or whatever may or may not be tested for these scenarios. What happens if they both fail together? What happens if they both fail together and they restart? Have you tested starting in both orders, or every time you test, you always start Cassandra and then you start Storm? What happens if you flip that? A lot of people don't realize how many corner cases there are as soon as you've even glued two systems together. So my main point of this kind of opening section here is that operational glue code is hard. Avoid it. And one of the ways we avoid it is transactional stream processing. And so what does that mean? Well, we start by saying use the same system for state and for processing, right? Make sure that they're tested together. That is, everyone who's using that stream processing system is using that state system and vice versa. They're not talking over a network. Everything is tested integration. It also means there's no independent failures, right? I'm not going to have, or at least if it's a distributed system with lots of processes, they've tested those failures together. You're not handling in your code the failure scenarios. The second thing we do is we say, if I've got an event processing system, I'm going to make one event processing one transaction. And so a lot like in the 70s when people first started looking at transactions and said, well, hey, this could make our data processing a lot easier, it applies just as well to stream processing. What the same things that make data processing in relational databases in the 70s and 80s easier with transactions makes event processing today easier with transactions. You get atomicity, and I'm going to go into these even more detail. You're either 100% done or 0% done. There's no in-between cases for you to worry about. Consistent is sort of a thing that doesn't really apply. It makes the acronym work well, and you can ask me about it later if you want. But the other two that are really important, isolated. Two concurrent operations can't interfere with each other. And durable, if it says it's done, then it's done. If you have these in your stream processing system, you can do more. So here's some processing code for a single event. It's separate from a database state, and it's going to go back and forth over the network. Say something fails here. Right? So now half of your work is done, and half of your work isn't. You actually need to go in somehow and figure out which half got done. Did all these things get done? Is it possible that the first and the third thing got done, but the second and the fourth didn't? This is a real pain to clean up with. It's much easier to manage these cases if you can't fail in the middle. You just fail entirely or not at all. So that's not atomic. And this is the slide that the VoltDB marketing department really likes, so I just kind of put it in here for their benefit. But if you look at an atomic operation and you're Juliet, and your plan is to fake your death and to tell Romeo about it, in the play, she manages to fake her death, but she fails to tell Romeo, and this does not go well for Juliet. or Romeo for that matter. If we're looking at isolation, maybe I have two events being processed at the same time. They're both interacting with database state. They both have these same sort of 4 operations, but they're interleaved. And I'm going to go into some of the sort of problems that you can run into with that, but that's something that we want to avoid. All right, so for the rest of the talk, I'm going to talk about a specific example. It's not a perfect example that covers every use case, but it allows us to talk about a bunch of things. This is an app that I actually worked on for a VoltDB customer. It's a call center management app. They've got millions of customers, 3,000 agents. What they want to do is keep track of things for billing purposes, so how long they were on the call, et cetera. And they want to create dashboards and alerts so they can understand the health of their call center. So customers and the agents are what are interacting here. And that interaction generates events. And the events are pushed into a system that does processing and state together. It supports the dashboards. It supports the billing. The 2 events that I'm going to worry about for this talk are begin call and end call. And the begin call basically has some metadata about the call and a start time. The end call has some metadata about the call and an end time. That's it for now. The real app is a little bit more complicated, but not much. This is the real crux of it. So if we take this app, which is fairly straightforward, and we want to look at what can we talk about in terms of this app, we can talk about correlation. Right? We need to find the ends and the beginnings and match them. We can talk about out-of-order delivery, because it's sometimes the end for a call comes before the start of the call. I can't guarantee that I'm going to get the messages in order for this particular app. I can talk about at least once delivery, right? If I've got the source set up to be an at least once delivery source, I may get doubles. I may get notified about a begin call twice. That's actually a good thing, because for the most part, in many cases, that's the best we can do. I want to generate a new event on call completion. So when I find the begin and the end and they match, I want to generate a new record, and I want to do that exactly once. I want precise accounting so I feel comfortable billing my customers and saying, yes, this is your bill. I want precise stats. And I want basically stats that have to do with event time, not processing time. If a machine fails and comes back 10 minutes later and then sends all the events that it didn't get to send while it was failed, I don't want a million call records to come and me to think that that's when they happened if they've actually happened over the past half an hour. I'm working on this example now. This is something that I got a little delayed on, but right now this is all public code, and I hope to have this in a future, in the short-term version of VoltDB as an example app, but it's here on GitHub if you want to browse some of this code. I'm going to be working on it over the next week or so too. The hardest part I found of building this example, not the begin call code or the end call code in Volt. The transactional streaming makes that very straightforward. But the actual client code, generating fake calls, basically that reasonably approximate real calls, generating bad network. So I sort of built this bad network transformer that duplicates and delays fake data. When I built this app with a customer, I was given logs with gigabytes of phone call data that I could just feed into Kafka and feed into Volt. And in this case, I don't have that because I'm trying to make a public example. So I'm trying to generate a data generator that could run indefinitely. It's much harder. OK, so correlation was sort of the first problem we put up. Correlation requires state. So let's talk about the state of this example. I've got a table called open calls, and I've got a table called completed calls. The open calls has all the unpaired events. Whether it's an end or a start, I didn't say what order they came in. I put that all in open calls. As soon as I match it, I move it into completed calls. That's all the schema for this application. I want to filter duplicates. And so the way I do this is I make my operations idempotent. So idempotence is a really cool thing in stream processing. And I said that sometimes the best we can do is at least once delivery. So if we have at least once delivery, we need to do duplication. And the best way to do that is to make my operations idempotent. So this is basically means if I do something more than once, it has the same effect as if I did it once. And so this is, I think, best to explain with examples. If I set x equal to 5, and I do that twice, x is still 5. Whether I do it once, twice, 10 times, x is still going to be 5 at the end. If I increment x, not idempotent. Incrementing x and incrementing x twice gives me different answers. Say if x is even, increment x. This I can do a whole bunch of times, right? It moves 4 to 5, but then it stays 5 for the next few operations. If I say it's even double it, it moves 4 to 8, and then it moves 8 to 16, and then 16 to 32, etc. If I spill coffee on my brown pants, I do this more than once, it's not so big a deal. If I eat a whole plate of spaghetti, there's a big difference in eating 1 whole plate of spaghetti and eating 2 whole plates of spaghetti. So this is sort of the how we get exactly once semantics. How we can say we're processing things precisely is by combining at least once delivery with idempotent operations. And it is a lot easier to get idempotent operations if you've got transactional stream processing. So how do we make begin call idempotent? Well, this is just basically the entire logic of begin call. If the call record is in completed calls, right, this is a call I've seen before, ignore it. If the call record is in open calls, but I've got the begin time already, right? I'm missing an end time still, and this event is the begin time. This is a duplicate begin time. I can ignore it then. And then I say if a call record is in open calls and it's got an end time, this will complete the call. I have to handle, this case handles the swapped begin and end. Otherwise, create a new record in the open calls table. So these ignores here, this is the idempotent code. Because this is transactional and it's either all going to happen or none of it, by putting these if statements with ignores here, and really if you look at the code, which is on that GitHub page, it's just this. It's not even that much longer than this. It's like 15 lines of code. Then this ignore basically means I don't do anything twice. And this whole logic here is a transaction. So now I get to the accounting and statistics bit. This is the part where I want to do billing and I want to get the right answer. So many customers come to us and they say that the bills they send their customers are mostly right, but they're not quite sure. And they want to be able to bill confidently. A lot of times people are being nice and they're underbilling their customers so that they know they're right. And sometimes people are overbilling their customers so they can have lots of money. But with actual transactional streaming, you can almost always get an accurate answer with billing. So counting in distributed systems is hard. This is another one of those things where if you type in counting is hard into Google, you're going to get a bunch of blog posts. This is one by Leif Walsh when he was at Tokutech. But it's really hard to do at scale. Machines are really good at counting individually on a microprocessor. They're really bad at counting in a distributed system with dozens or hundreds of nodes. So there's two kinds of fail. There's miscounts and there's extra counts. You cross your fingers that they cancel each other out, but it doesn't make you feel super comfortable. One of the ways that you can get this is from poor isolation. So here, this is the most basic example. I've got incrementer 1 and incrementer 2, and they both read x when it's 27. They both say I'm going to write 28 because that's the increment, right? And then they both write 28. And what happens is I've got 2 incrementers, but I've only incremented the value once. So that you get from poor isolation. Oops, wrong button. And that goes sort of back to this slide, the not isolated slide. If I have interleaved operations, I can't guarantee I'm going to be able to do math correctly. So what systems can do counting? Systems with single key consistency, where I basically have like a transaction on a key kind of system. Those systems can update a counter safely. If I've got systems with special features to enable counters, like Apache Cassandra, for example, those systems can do counting. If I've got an ACID transactional system, obviously these systems can do counting. However, if you have a system that says we're an ACID transactional system, and then you look and you realize actually they can only support read-committed isolation, that doesn't help. So when you look for a system that says it's ACID, look at what levels of isolation does it support. When they say that they can do this much performance, are they saying that they're doing that under read committed, under snapshot? In what kind of isolation model are they using? And also systems that enforce a single writer can do counting. So as we say in New England, the performance of these systems is wicked variable. And when I say that, I don't mean an order of magnitude, or 2 orders of magnitude, or 3 orders of magnitude. I mean like sometimes 4 and 5 orders of magnitude difference in performance. Depending on your deployment structure, depending on how you built your application, you may be able to successfully count things, but man, is it going to take different amounts of resources and have different ceilings. Accounting. Accounting has the word counting in it because it's basically just fancy counting. Maybe you need to be able to increment by an amount or decrement by an amount. maybe you need to increment decorate things in groups. And groups is really the interesting thing we want to do. When we want to move from simple counting to really interesting accounting, we need this groups functionality. So here's an example of a user playing a video game, some kind of online multiplayer game, and they've bought a mystical sword of hegemony. So when this happens, what we need to do in the system, we need to debit the gamer's rubies, or whatever the currency is in the game. We need to update the real-world region stats. So maybe we count how many swords have we sold in the Asia-Pacific region, right? How much money have people spent on swords in the Asia-Pacific region? This is an interesting counter for us, an interesting value for us. Maybe the in-game has regions as well, right? You don't want everybody who's running around in the same part of the game to have the same sword. Maybe if everyone in the Tar Shoals of Dintimore has too many of these mystical sword of hegemonies, maybe you up the price at the store, or you stop selling them. You can balance the game, and it's amazing how sophisticated all of these sort of massively multiplayer iPhone games get at changing the game based on live conditions. This is not the system where they ship a ROM to you and you start playing it on your Nintendo. These are games that are very dynamic in response to what's happening in the game to keep you engaged. And specifically, you've got things like offer-related stats. So maybe that sword was bought to you because we decided to run an algorithm that temporarily dropped the price of swords. We want to correlate you buying that sword or not buying that sword with that offer, with the offer that we were running at the time. So that way we can track performance of different algorithms and decide if they work. It's a lot like high-frequency trading, really very, very similar. And so if this is not atomic, and I do half of those things, I debit the rupees, but I keep track of all the stats, it's going to be really a mess to go in later and try to update the stats. I basically, if I've got a whole mess of counters, and sometimes you see 10, 15, 100 different counters that get updated for a single thing that happened, figuring out which one of them were incremented by 1 and which one weren't, when you've also got 500,000 other people playing the game at the same time, can be really challenging. So atomicity helps a lot here. So once you move to accounting, this rules out systems with single key consistency. It rules out systems with special features to enable counters. That is, you don't get atomicity for these systems. So some of the counters might be updated, some of them might not. You still get ACID transactional systems. If you've got systems that enforce a single writer, this is a maybe. You don't have atomicity by default with systems that enforce a single writer, but it's easier to code. It's not fun to code, but it's possible. And again, performance, really different. Before I move on past accounting, I just want to mention the last dollar problem. I'm not sure if this is a general term for this problem, but it's something that we call it at Volt because we see it over and over. Say I've got an ad tech app that wants to show a user an ad from a campaign. It says, I think that this is the best ad to show this person. And I go look, I see the price of this ad is 90 cents. The campaign that I want to show this ad from has $1 budget left. Do I show the user the ad? All right, my 6-year-old is going to say yes. But the catch with this is that if the budget check and the display aren't ACID, if these are not, it's not a transaction tying these things together, it's possible to show the ad twice. So you've actually got a choice here. Do you show the ad twice and only bill for one time? You lose some ad space that you could have used that space to show a paying ad. Or do you not use the last dollar in the balance? You just basically, when you get to a certain threshold where it gets low, you say, I'm going to give you that money back because I'm not sure I can safely use it. And we've talked to a number of ad tech companies where they actually do the latter. If you get down to $1 and you've got all these ads that cost $1, they won't do that because they're not sure that they can safely do that. They'd rather show a different ad in a campaign that has budget. And this last dollar problem is not just an ad tech problem. We've got a similar problem with one of our CDN customers who's billing based on how many HTTP requests you make from their CDN network. Until Volt, they were basically saying, we don't really know that the billing is accurate at the end. Aggregation, this is basically just counting that the system does for you, and it's often chopping things up by groups, right? So you want to know sword sales by region, percent success by offer. A lot of times if you've got aggregation, you can do these counters yourselves, or you can tell the system, here's the aggregation I'm interested in, make it happen. In the call center example, it could be average call length by agent. So aggregation, we've got systems that enforce a single writer. It's all the same as counting. As accounting. It's not fundamentally different. If you can do accounting, you can do aggregation. Well, what if you don't have transactions? How do you do aggregation? Because people do a lot of aggregation. It's one of the most popular things we do with streaming systems. So if I have a standalone stream processor, a lot of those systems have aggregation engines in them, or can use off-the-shelf aggregation engines, or you can write one if you want to. These work decently if you're aggregating time series data. And specifically, they work best if you're comfortable processing things at the time they arrive, as opposed to the time the event happened. It's a lot harder if things are coming way out of order to process things in standalone stream processors. This is a huge generalization I'm making. There are exceptions to lots of this. I'm happy to talk details. I'm making kind of a blanket statement, but not a false blanket statement in many cases. You can also say, well, a lot of this time series data, a lot of this event data, it's immutable once you've sort of processed it. So I can run queries on the data every time you want the aggregation. This says basically I want to do these aggregations in batch mode, which is perfectly fine. But it's no longer sort of operational. It's no longer sort of latency sensitive. It may be harder for me to use those aggregations to make decisions. So it's sort of out of the purview of what we're doing here. All right, so the last thing beyond aggregations, and this is the thing that gets a lot easier with transactional streaming that's really, really hard to do with lots of other kinds of streaming, is actual math. So say someone says, well, what's the mean and standard deviation of call length chopped up various ways? Okay, mean I can do, right? That's just summing and dividing. But standard deviation, I look up this formula for a standard deviation of a population, and I go, ooh, there's a the square, the differences summed. That's going to be really hard because the average is going to be changing. So I go to Wikipedia and I look up standard deviation. I can find that there's actually ways to calculate a running variance, so I can incrementally do this. And I can come up with a function that will get me an incremental standard deviation based on a calculation from the previous event and the current value of the current event. Doesn't matter, right? The details don't matter. The idea is I found the math, I figured out how to do it. I still need to think about performance, right? Is this math I can do reasonably quickly? And that math I can do that reasonably quickly. It's just floating point stuff. And I do have to think about partitioning my work, right? If I've got 100 clusters, it may be that I need to think a little bit about how I'm going to partition that work. But the things I don't have to think about, I don't have to think about failure management. I don't have to think about interference from weak isolation, right? I can just write the code for the math. And if I think this is going to work in a partitioned scenario with reasonable performance, then I don't have to worry about all this other stuff. It's never going to fail in the middle of an equation. It's going to do the whole equation or it's not. And I don't have to worry about as much partial visibility of state, right? If one of my nodes fails and I only see half the data, am I making a decision based on half the data? I don't have that situation. Bonus topics for the last few minutes here. Number one is latency. One of the benefits you get from integrating processing and state is lower latency. And what kind of things can you do with lower latency that you can't do with a stream processing system with high latency? Well, the goal is sort of to jump into the action, jump into the decision, put yourself at a low enough latency that you can help make decisions. So here's an example that I worked on where you swipe a credit card and you want to know if it's fraudulent before the credit card goes through or not. All right, this system was using a fraud detection solution over here that after the fact would figure out whether things were fraudulent and then put a hold on the card. So they basically had this situation where if a card was stolen, you could use it once or twice and then it would stop working. What you really want to do is be in between that card swipe and the bank and be able to catch a lot of the fraud there. You may not be able to do as many really sophisticated machine learning things in 500 milliseconds, but certainly you could take a lot of machine learning on the fraudulent, non-fraudulent data, load those rules into a transactional streaming event, and give what I call like sort of a fraud smoke test, where you get most of the fraud benefit, but in a much, much faster kind of real-time system. And almost all the banks in the US use a real-time system like this. Other places you can sort of get into the fast path, you can jump into the decision. Policy enforcement and telco. Am I allowed to make this call? Fraud detection, smoke test, as I mentioned. You can change what a user sees in response to action. And I think this is a huge, huge thing. We see this a lot in gaming, but we're starting to see it a lot in customer engagement solutions. Whether you're making websites, apps, keeping a customer engaged, the same way that Candy Crush has figured out how to keep you engaged by changing the game based on what's going on to keep you playing at all costs. You see things like airline frequent flyer miles changing what website they're drawing to you. You're seeing different content based on what you're browsing in order to keep you engaged. You may get a different offer, a different layout even. They're just experimenting, trying to keep you engaged, and you need to be able to jump into the action between a user clicking a link and drawing the page the user sees. And the last sort of bonus thing here is, does your data actually matter? And this is sort of a weird, hopefully a conversation starter. The example problem we talk about, say you've got a factory full of robots. Sometimes they break and they log all this metadata. And you've just built this factory, right? So right now, you're not collecting the metadata. Maybe you are, but you're not doing anything with it. Your maintenance staff works on stuff based on their experience, which shouldn't be discounted. Maintenance schedules and visual inspection. So you build sort of a stream processing system to churn on that data, and it's up most of the time, and it provides much richer guidance to maintenance. Robots fail less often and cost less to operate. This is a huge win, right? You've just saved a lot of money because these robots are expensive. So a possible future is I want to move to a more sophisticated stream processing system. It's up more of the time. It offers more insight. Robots fail a tiny bit less and costs are a tiny bit down. So this is sort of the, it's going to be challenging to say, is it worth changing my system from one that kind of mostly works and gets me a lot of value to one that gets me a little bit more value? How do I make that decision? This is sort of an example where I'm not sure I would. It depends on how things are running. What we really like is to be able to say, the possible future is easier to do than the now. And that's what we're working on. But in a lot of cases, it's obvious. And I use this formula to look at, does it make sense to avoid systems that are kind of fuzzy, a little bit imperfect, for a system that gives you more confidence in your answers, a transactional system. So first start looking at the cost of the system, which is often not the most interesting thing. And that includes licenses, hardware, people, and it also includes any costs from switching from what you have now to the new system. And then you've got this sort of other stuff over here. Oh, hold on, let me get rid of that. You've got this other stuff over here, which is the number of operations, the probability of failure, and the expected average failure cost, right? If any of these is high, and the other two are not close to zero, then you're in trouble. So there could be that the expected average failure cost is high, but the other two are very low, like close to zero. In that case, maybe it's not a big deal. It could be that your number of operations is astronomical, but the other two but the probability of failure is close to zero, or the expected average failure cost is close to zero. In that case, it's not worth it. But I'm using the wrong button. There are a lot of cases where one of these things is very high and the other two are non-zero. So ad tech use cases I've worked on, they have a tremendous number of operations. The probability of failure varies, not zero. And the expected failure cost, maybe it's 50 cents, maybe it's $1, maybe $1.50. Not particularly expensive, but when you multiply it by the number of operations and the fact that you're running 24/7 forever, it's a huge amount of money. Tremendous. Complex multi-cluster systems and monsters. You went a little overboard at the Apache buffet, and you've got 9 different clusters running right now. Your system is barely up. If your expected cost of failure is not zero, and the number of things you're doing is not zero, then you basically, you're going to end up with a very expensive system. If you have billing systems and fraud systems, a lot of these cases, the expected average failure cost goes way up. Right? If someone is fraudulently buying a laptop, that's an expensive failure. Even if that failure is only every 10 million entries, if I'm doing 100,000 things a second, that adds up pretty fast. Basically, really things that are very, very infrequent, if you're doing things at scale, suddenly become frequent. And the last point on this is that more consistent systems don't have to be more expensive. This isn't a case where I spend more money to get more. A lot of times with more consistent systems, you have less engineering work because there's easier to develop. A lot of times you have less hardware because these systems are more efficient. It's not a linear thing where you're saying, I'd like better answers, but I can't afford it. Sometimes there's switching costs and things where you need to think about that. But overall, it's worth looking into sort of to do this math for yourself for any problem that you have. OK, that's the end of my talk. So my conclusion here is that for operations, it's really important to have integration, to have things all be tested together and be very smooth and reliable. For analytics and batch, specialized tools are great. with transactions, basically a lot of the math becomes very straightforward. A lot of the how do I do that is just typing. And there are a lot of ways to solve a lot of different problems. But without transactions, just like in the 70s and 80s with the relational databases, same thing with stream processing. It's going to be harder, and it's going to be less accurate. So certainly reach out to me if you have feedback on this talk. We have a few minutes, I think, for questions. If you want to chat up VoltDB, we have a Slack channel like everybody else. Come to the VoltDB booth up in the pavilion. We're giving out tattoos, spray tattoos of open source logos. So if you want an elephant or an Apache feather, it lasts about a day. They're pretty cool. We've got a bunch of a tattoo artists over there. Even if you just want to watch, it's a pretty cool thing. And we'll all be over there answering questions. So thank you very much for coming to the talk. I appreciate it.
All right, thank you. Thank you very much, John.